So far in our course we have been talking about analog electronics, and now we are going to start the second part of our course, which we are going to discuss the digital electronics. What's the difference between analog electronics and digital electronics? Analog electronic circuits are circuits that deal with analog signals. Digital electronic circuits are circuits that deal with digital signals. So now we ask the question, what is the difference between analog signals and digital signals? Analog signals are signals whose amplitude, let's assume it's volt, can take any value. So this is called analog signal. The amplitude can take any value. This is an analog signal. While a digital signal is a signal whose amplitude can take only finite number of values. For example, I say that this signal, its amplitude can take either 1 volt, 3 volt, -1 volt, -3 volts. At any time, it has to be at one of these 4 levels. So this is finite number of amplitudes. So for example, here it will be 1 volt, then here it will be -3 volt, then 3 volt, then 1 volt. This is called the digital signal because the amplitude cannot take any value, it can take only finite number of values. So this is called digital signal. Okay, so now we are going to discuss circuits that deal with these digital signals. And when we deal with digital signals, we deal with something called the logic gates. And the most famous digital signals are the binary signals. The most famous logic or the most famous digital signals are binary, which can take only 2 levels. Binary means 2, bi means 2, right? Binary means it's a signal with 2 levels, high or low. So the most famous logic that we are going to focus on in our course is the binary logic. And we are going to study logic gates, how to implement these logic gates using the electronic circuits or the electronics that we learned in our course. Of course, digital electronics can be found in many devices. For example, now everything in our life is based on digital electronics. Your digital receiver, your computer, your TV, your many things are based on digital electronics. The design of digital circuits has progressed. In the beginning, it was based on something called resistor-transistor logic. It's kind of logic family or logic circuits that were based on resistors and transistors. And then diode transistor logic, DTL, appeared, which were circuits that were based on diodes and transistors. And then we moved to transistor logic, TTL. All of these are different families or different designs of logic gates. RTL, resistor transistor logic, DTL, diode transistor logic, so they design based on diode and transistors. Here, TTL, they designed the whole logic gate based on transistors, and then appeared emitter coupled logic, and then complementary MOSFET, or basically CMOS. So we can classify, currently we can classify the different logic families according to this tree, where we have some logic gates based on the MOSFET, and some of them are complementary MOSFET logic, pseudo NMOS, pass transistor logic, dynamic logic. So all these are different designs or different families based on the MOSFET. And then there is another family based on the bipolar junction transistor, similar such as the TTL, transistor logic, emitter coupled logic. And then there is another family called the BiCMOS, and a fourth family called gallium arsenide. Here in our course, we are going to focus only on the implementation of complementary MOSFET, implementation of the logic gates using the complementary MOSFET, and also at the end we are going to discuss the pass transistor logic. So this is what we are going to focus on in our course, the complementary MOSFET, CMOS, and the pass transistor logic, and both of them are based on the MOSFET. Of course, as I said, we are going to focus on the binary logic. Although digital is wider than binary, digital is a general digital electronics or digital signals are more general than binary, but we are going to focus only on binary, and binary means you have high or low, only two levels, high or low. Okay, and when we say high or low, this doesn't mean 0 or 1. 0 or 1, so high means 1 in logic, and 0, low means 0 as a logic, but it doesn't mean 0 and 1 as a volt. So when I say high level, which is 1 in the binary logic, similar to what you studied in the logic circuit course, in the logic circuits course, the EE200, when you say high level or 1 in the logic 1, this doesn't mean necessarily 1 volt. It doesn't mean 1 volt. It can be 5 volt. It can be 10 volt. It can be some high level, V plus. Same when we talk about the low level means 0 logic 0. This doesn't mean necessarily 0 volt. Doesn't mean necessarily 0 volt. It can be any low voltage level. It can be 0, or it can be -5, or it can be -10. So it can be anything. So when you hear the word logic 0 or logic 1, this doesn't mean that the voltage is 1 or the voltage is 0. It means that you have a high voltage level and a low voltage level, and these levels can be anything, V plus, and let's call them in general V plus and V minus. Now, when we study the logic gates or we study any logic family, the most basic building block of any logic family is the inverter. Which means that if you can build the inverter, then you can build any other logic gate. That's why we are going to focus on building the inverter. And the inverter, this is the symbol that we use for the inverter. We use this symbol to represent the inverter. It's a triangle, maybe with a bubble at the end. And this is the input, this is the output. And then the inverter, it has two levels, high level and low level, V plus and V negative. So let's call it V plus, V subscript plus, and V subscript negative. So this is the symbol of the inverter. And the ideal inverter, the characteristics of the ideal inverter is that when the input is lower than a certain reference level, then the output will be high. So when the input is low, the output will be high. When the input is high, the output will be low. This is the characteristics of the ideal inverter. Ideal inverter. When I'm saying ideal, the word ideal means what? Means this is the perfect inverter. This is what we dream to have. But unfortunately, as we will see, practically speaking, we will not have such a nice characteristics. Okay? So the ideal inverter, it has characteristics or relation, transfer function between the input and the output that looks like this. When the input is low, the output will be high. When the input is high, the output will be low. And then there is a sharp transition between the two levels. This sharp transition happens at a certain reference voltage. This reference voltage determines whether the input is considered to be high or considered to be low. If the input is lower than this reference voltage, then it is considered to be low. If the input is higher than this reference voltage, then the input is considered to be high and the output will be low. So, as I said, the inverter is the basic building block of any logic gate. So if you can build the inverter, we can build any other logic gate. Okay? V plus and V minus here, these are the high level and the low level. So for example, when you say in the inverter, if the input is low, then the output will be high. If the input is logic 0, then the output will be logic 1. Then here, in this setup, the logic 0 means low level. Low level is V negative. We say that the output will be high, logic 1, and logic 1 here means V positive. So here logic 0 and logic 1, they are represented by a voltage levels V negative and V positive. Okay, where V negative and V positive are the supply voltages used in the circuit that we design for this inverter. So when we design this inverter, we use some elements inside like transistors, like resistors, and voltage supplies. So V plus and V negative are the voltage supplies used to design the circuit of the inverter. A simple way or an example to show you how to implement an inverter using transistors, so is to bring a switch. In order to just like implement an inverter, you need a switch. And this switch, in this setup, for example, we have voltage supply V plus, we have here the other voltage supply, the negative voltage supply here, V negative, we choose it to be ground. And then if you have a switch here, and this switch is controlled through V input. For example, if you design this switch so that it is open when the input is low. So you can design this switch so that when the input is low, the switch will be off or open. Then what happens when the input is low? The switch will be off or open, and if the switch is off or open, what happens? There is no current that will go in this circuit, and if there is no current that will go in this resistor, then V output will be equal to V plus, which is the high level. So now, when the input is low, the output is high. On the other hand, if we design this switch also so that it will be on when the input is high, so when the input is high, the switch will be on. On means it will be closed, short circuit. Then when the switch is on or closed, short circuit, then the output will be connected by a short circuit to the ground, right? To the low voltage supply. So output will be connected to the ground or to the low voltage supply. So V output will be equal to V negative, which is the low voltage level. And V negative in our case here, it's ground. And just to be consistent, V plus here, we write the plus down, okay? So here, when the input was low, the output was high. When the input is high, the output turned out to be connected to the ground or to the low level, right? So this is the basic idea of an inverter. We can implement this switch using a transistor. For example, we can implement it using a MOSFET or a bipolar junction transistor. If we implement it using a MOSFET, then when the input is low, it's not enough to operate or to make VGS greater than V threshold, then this transistor will be off. So when the input is low, this transistor will be off and the output will be equal to V plus, to the high level. When the input is high, this transistor will operate, and you can choose the resistance here so that when the transistor operates, it operates in the triode region. In the triode region, VGS will be very small, so you can choose the load line, your load line, so that the operating point will be here or here in the triode region, and it will give you VGS very small. So when the input is high, you can design the transistor to operate in the triode region so that VGS will be very small. And VDS is what? VDS is V output. So V output, which is equal to VGS, will be very small. So when the input is high, the output is small. While when the input was small, the transistor was off and the output was high. Similar to that, we can use the bipolar junction transistor. If the V input is very small, it's not enough to operate or to provide 0.7 for VBE here, then the transistor will be off and V output will be equal to V plus. So when the V input is low, V output will be high. When V input is high, this transistor will operate, and you can design the transistor, or you can choose this resistance, the load line, so that this transistor operates in saturation. And when the input is high and the transistor operates in saturation, the output will be equal to VCE. The output will be equal to VCE saturation, which is in the range of 0.2 0.1 or 0.2, right? So when the input is high, then the output will be low. So this is a basic idea of how to implement the inverter using just one transistor and one resistor. Of course, this is a very simple idea. This is what they called in the old days, they called RTL, resistor transistor logic. They implement the inverter using a resistor and transistor. Okay? So this is just to give you an idea of how to implement an inverter. Anyways, as I said, for the inverter, the ideal characteristics are the relation between V input and V output. It looks like this, right? With a sharp transition between the high and the low. We'll see in this slide, we'll see in practice how the characteristics, how the transfer function between the input and the output looks like. We'll see that in the next video, inshallah.